Hello, hello. I hope you're doing well, having a great day. My name is Taha. I'm here to explain a few topics. Feel free to ask me any questions if you'd like. Feel free to interrupt me as well if there's anything unclear. Be more than happy to explain it in a lot more details. Have you ever wondered why does the temperature in Toronto follow a predictable pattern every year? For example, why does a Ferris wheel height repeat perfectly? What today we will cover is modeling real life situations using sinusoidal functions. Let's start with explaining, quick refresh, what sinusoidal functions are. You might have seen this equation. Let's first start by writing the day. You might have seen this equation before, which has the form y equals a sine bracket k bracket x minus d close two brackets and then plus c. You might have seen this equation before. That's what we call a sinusoidal equation. However, sinusoidal equations, they actually do refer to any function like sine or cosine that behaves similarly to sine. So it keeps fluctuating up and down. So another form for sinusoidal equations, which you might be familiar with as well, is a cos k x minus d and then all plus c. So we have those two forms. As a quick recap, let's try to review what each parameter meant. We have the a, for example, that is the amplitude. In other words, how high the wave goes. We have the k, that's the next variable, that is related to the period. So like how long does it take to complete one cycle, one full cycle. But remember something, k and the period are related, but in a sneaky way. So k is 2 pi over t, where t is the period. So whatever the period is, whatever how long it takes to complete one full cycle, to get the k value, you just have to take 2 pi divided by the period. The next parameter we have is d. That one is a bit tricky as well sometimes. That's called the phase shift, or more commonly known as a horizontal shift. That's basically how your wave shifts left and right on a graph. The last parameter we have is the vertical shift, which is like how your graph goes up and down. You shift it up and down. Sometimes we refer to it as a midline as well. Great. Quick recap. If you have any questions, feel free to ask me about those two functions. If not, we'll continue to our first problem, first word problem. A Ferris wheel has a diameter of 20 meters and its center is 12 meters above the ground. Completes one full revolution or one full rotation every 40 seconds. A rider starts at the bottom. Write an equation for the rider's height as a function of time, then find their height at t equals 55 seconds. So that's a very interesting problem, which shows you how powerful math can be if you want to model where someone is going to be at any given point, if they're on a Ferris wheel, of course, which is a very interesting problem. Let's write down some givens. I like to write them down explicitly. We have in this problem, for instance, the a value, similar to what we've been doing before, which is the amplitude. Now you might say the amplitude is 20, but bear in mind, if you have a Ferris wheel that looks like a circle, like this one, and the diameter is 20, this whole diameter is 20, we're only interested in the radius because that will represent the amplitude of rotation as it rotates around. And so the radius, which is the amplitude, in this case, that would be 20 over 2, which is 10 meters. Now, I know this might be a little confusing. Feel free to ask if you have any questions. If not, we'll continue. The next parameter that we can figure out is actually the center, 12 meters. So we have that C, which is the center or the midline. That is 12. Let's keep them as numbers for now. That is 12 because that's where the middle point is, right? So far, so good. All right. We also have something related to the k. We do have the period as 40 seconds, but remember, the k value is 2 pi divided by the period. So the k is 2 pi divided by the period, which in this case is 40 seconds. So 2 pi divided by 40. We can simplify this because it's always nice to simplify, and that becomes pi over 20. So far, so good. Right. Now to identify the d, we first need to know what function we're dealing with here. This Ferris wheel, we said, starts at the bottom. So we want a function. When we put the t0, it already starts at the bottom. Let's take a look at Desmos, for instance. If I write down sine x, you'll see that sine starts from 0. It doesn't start from the minimum point, but we want to start from the minimum point because as you can tell, if you're in a Ferris wheel and you're at the bottom of the wheel, you're basically starting from the middle. You don't start from the middle of the Ferris wheel. So you want to start from the bottom. But then if I try to sketch cosine x, you'll see that cosine starts from the top. Now there's a very neat trick that we can actually make cosine start from the bottom, and that is by taking the negative of cosine. And now look at that. When we have the x-axis, the x value is 0, we actually have a y value of -1. So we're starting from the bottom. So our d will be 0 because we will take negative cosine as our function. Okay, now let's try to put this all together so we can actually model this. We have our a, the form that we have is y equals a cos. Now we're using cos. A cos, we have k x minus d plus. We said we're taking negative cos, and the a is 10, so we're actually taking our form here. Let me write it down. Y equals -10 cos. The k we found was pi over 20. Sorry, I had a little typo there. Pi over 20. So we have cos pi over 20 x minus the d, which is 0, so it's just x, and then plus c, which is plus 12. Okay, and it's always good to like see what this graph would actually look like on Desmos, so let's try to sketch it. So we have -10 cos pi over, oops, pi divided by 2 multiplied by x plus 12. And here you'll see this beautiful graph that actually models our Ferris wheel. So as you can see, it does start at the bottom at 2, which is where the person might get onto the Ferris wheel. And then they'll go all the way to the top. That's you can reaching all the way to the top of the Ferris wheel, and then coming back all the way down and back at 2. And then the cycle keeps on repeating because again, you're going in a circle, you keep repeating the sinusoidal function. Your maximum is indeed at 22. And your midpoint would be around 12. So we can sketch this, y equals 12. That's your middle point, or like your equilibrium line. Okay. Let me know if you have any questions. If not, we can move on to the next example. Okay. We have another example here, which shows you that the average monthly temperature in a city, maybe like Toronto, reaches a maximum of 28 degrees Celsius in July. I know it gets really hot in the summer, and a minimum of -4. Maybe not a minimum of -4. Sometimes it gets a bit colder in Toronto, but for the sake of this problem, let's say it's -4 in January, which we'll treat as month number 1. Let's write a sinusoidal equation to model the temperature as a function of the month that we have. First things first, again, we will write down our givens. So how do we find the amplitude? How do we find the amplitude A in this case? Well, it's actually a very easy equation. All you have to do is take the maximum value minus the minimum value and divide by 2. So what was the maximum temperature that we have? That was 28. What was the minimum? That was -4, all divided by 2. As a quick recap, you might know that 28 minus -4, that's the same as 28 plus 4 all over 2. Because minus minus becomes positive, which becomes 32 over 2, which is, let me make some space here. Oops. All right. Which would be 16. That's our amplitude in this case. The C value, be careful, it looks very, very similar to the amplitude, except for one difference. It is going to be the maximum plus the minimum over 2. Okay, so just bear in mind, they look very similar. They have one difference, which is their sign between the max and the min. So the maximum temperature, again, was 28 plus, we're using plus this time, the minimum temperature, which was -4, and then all divided by 2. 28 plus -4, that's the same as 28 minus 4, which is 24 over 2, which simplifies to 12. So far, so good. Let me know if you have any questions. The K value, we can figure that out from the period. The period is 12 months, of course, because the seasons repeat every 12 months. We're using months here. And so we can say that it is 2 pi over the period. Since the period is 12, this becomes 2 pi over 12. We can simplify. How can we simplify? We can divide by 2 up and down, which gives us pi over 6. Okay. All right. Now to figure out the D, as you can see, we are starting from a minimum, which is January, because January has the minimum temperature of -4. However, we might do this in another way, and I want to introduce you to the other way, just so that you can have both ways in your pocket whenever you're facing these kind of questions, whichever you're feeling more comfortable with. We can say that, well, we know the maximum happens on July, which is month number 7. So we can shift the cosine function by 7. In other words, your D becomes 7. And now constructing your equation, it becomes y equals a cos. Oh, we're using cos, of course, because we know we're starting at a maximum, just like we saw in the other graph. A cos k x minus d bracket plus c. Plugging all our values that we just found out, which is most of the heavy lifting that we've done so far. Now it's just plugging in. That becomes 16 cos. The k that we found was pi over 6. X minus the d was 7. And then plus 12. And that beautifully models the temperature in a city like Toronto. Let's take a look what this looks like. Making that down. So we have 16 cos pi over 6 multiplied by x minus 7 plus 12. And as we can see here, this is the equation that we have for the cosine. And as we can see here, let's take a look. Sorry. Compare and contrast. Here at month 1, which is in January, we do end up with the minimum temperature of -4. And we do have a maximum in July, which is month number 7. We have it here as 28. The middle line is also 12. So we can sketch that here. Y equals 12. That's the middle line. And there we go. Now I would provide you with similar problems, or I can even ask you to come up with your own problem so that we can actually work on them. But before we do so, let's try to wrap up a few things. One of the biggest common mistake that students would make, which I want you to avoid, is forgetting to do 2 pi over period for the k value. So just remember that k is equal to 2 pi over period. This is a very common mistake. Another thing that I would like you to do is to be able to feel comfortable with choosing the sinusoidal function that you're going to be dealing with. You have sine, you have cosine. How do you know which is which? That will be dependent on the question. The question starts from 0, like you start from the ground. It's perfectly fine. But if you start from a minimum or maximum, you would probably want to use cosine. Okay. Another thing is to remember the steps that we were doing in like identifying those variables. Basically, we first found the A, the amplitude value. Then we went ahead and tried to find the C. Then we try to find the K, which is related to the period. And then we try to find the horizontal shift, which is D, depending on which function you're using. There's not one single way to do a problem. There's many ways that you can do this because sine and cosine are repetitive. With more practice, you'll feel more comfortable. I'll be more than happy to provide you with a bunch of similar problems and different ideas in the world around you. Just think of anything that repeats. You can definitely model it with a sinusoidal function. Okay. All right. Any situation can be modeled with these functions. So if you'd like to think of tides, sound waves, seasonal patterns, anything that makes repetitions, and that is really why sinusoidal functions are one of the most important functions that are super duper powerful. Okay. I hope that was helpful for you. Do let me know if you have any questions. If you face any difficulty with your homework, feel free to send me your homework and I'll be more than happy to take a look. And then we can do similar problems in class. That way you'll feel more comfortable. I'd be more than happy to assign you some homework as well. If you have the time, just do let me know. Okay? All right. I hope you have a great, wonderful rest of your day and hope to see you soon. Bye-bye. Thank you very much, and I hope you enjoyed my lesson. This was Taha. Nice to see you again, and hope to talk to you soon.